Good morning, one and all. My work is to study the exciton energy in an indium phosphate zinc sulfate core shell quantum dot nanostructure. This is the outline of my talk. Coming on to quantum confinement, first figure represents the bulk material in which particles can move in all possible directions. Second one is quantum well, in which particles can move only in two axes. Third one is quantum wire, in which particles can move only in one direction. Third one is quantum dot, in which particles cannot move freely. This can be achieved by reducing the size to 10 nanometer, which will change the electronic and optical properties of the sample. This kind of quantum dots can be synthesized from semiconductors as well as metals. So, the band gap increases as the size of the nanostructure decreases. The energy levels are discrete by reducing size. The color of photoluminescence changes from red to blue as quantum dot diameter is reduced from 6 to 2 nanometer. So, this is a nanostructure of core shell quantum dots. So, I have taken indium phosphate as core and zinc sulfate as shell. The shell material should have higher band gap and non-radioactive recombination process. By considering the edge alignment of conduction and valence band, these quantum dots are divided into 4 types. So these are the properties of indium phosphate zinc sulfate core shell quantum dots. It has wide range of emission from 500 nanometer to 800 nanometer. So due to large exciton bore radius. So group 2-4 type semiconductors have size tunable absorption and emission spectrum. And it is this kind of quantum dots have uniform size distribution, exotic optical application, photoluminescence, high quantum yield, etc. So this water soluble indium phosphate zinc sulfate quantum dots are safer, alternate to cadmium selenide zinc sulfate quantum dots. So now many of the biological applications uses these kind of cadmium quantum dots. But these cadmium quantum dots leaches cadmium 2 plus ions, which is toxic. So indium phosphate zinc sulfate core shell quantum dots can be used alternative to cadmium material. So these are the applications of my material. So coming on to background motivation. In this work, the temperature dependent exciton energy as a function of dot radius, that is core radius of the indium phosphate zinc sulfate core shell quantum dots are carried out. The electric and optical properties of quantum dots can be improved by external perturbation. Perturbation is the disturbance we are giving by an external force. The thermal behavior and fluorescence spectral shape of indium phosphate zinc sulfate quantum dots are studied. The temperature range has been taken between 7.5 Kelvin and 295 Kelvin, which is subjected under pulsed UV radiation. These are the perturbations we have taken. So, and how the exciton binding energy reacted to these perturbations are calculated. So this is the Hamiltonian equation of the exciton, that is strained exciton. So by applying perturbation, the excitons get strained, and then the parameters in the equation gives the values of the exciton. This Hamiltonian operator acts on the wave function and gives the eigenvalue of the electron and hole. So we have considered here the value in the single band effective mass approximation. and all the calculations are done by variational formalism. So this is how energy band gap difference is calculated. The strain effect induces an extra potential and confined potential is calculated, and V0 is the offset potential. So by considering all these values, energy band gap can be calculated. So this is a trial wave function we have chosen. From this wave function, we could able to calculate the energy eigenvalue of electron and hole using the Bessel's function, and by solving this transcendental equation, we could able to find the lowest binding energy of the electron and holes. Take into consideration of conduction and valence band around pi valley and matching trial wave functions and derivatives at boundaries of the quant dots has to be taken into consideration. And using all these values, we could able to get the binding energy of the exciton. So we all know what is exciton. That is a bound state of an electron hole which are attracted by the Coulomb force. So in the result, we have plotted the graph by varying the temperature and core radius and studied the binding energy. So binding energy increases with decreasing dot radius. It reaches a maximum value and then rapidly decreases due to Coulomb interaction between electron and hole. The excitonic binding energy decreases with increase of temperature due to increase in dielectric constant. So by taking all these values, we can able to design a novel optical device based on excitons. So finally I conclude, so these parameters these values help us to design a novel material, and group 3-4, group 2-6 compound semiconductors are promising candidate to replace cadmium material. Thank you for listening.